be the middle 50%, right, or the middle 68%? You would say one standard deviation either side. What would be the top 2.5%? Well, look at your little picture and say, okay, at this number, everybody to the right adds up to 2.5%. So it's really a bit like you've got a big cake and you're trying to find out what pieces of it add up to 5% or 12% or 32% and choose the number that would equal to. So let me show you very quickly a very simple version of what I'm getting at. Right, so here is the guy. Let's suppose the mean is 100 and the IQ is 10. And this middle chunk from here to here is 68. So that balances out as say 34, right? This little piece at the end, right? These two pieces here, right at the extreme ends. Well, 99.7, take away that. So each one of them is 0.15%. This one is 0.15%. And then you get another one that fits in here and then another one that fits in there. Now, I don't have time if, you know, do them all, but you can figure out what they are. So let's suppose you get a question and it says something like this. What IQ score would you need to be in the bottom 26%? Now, since you're talking about the bottom, I would be saying that guy, that guy, that guy, maybe that guy. How many of them add up to 26%? Can you trust me, although I don't have the three numbers, these three guys, if you added them up, would be 26%. So your answer in that question would be that an IQ of 90 would put you in the bottom 26%. Now, let's suppose, let me just tell you that that guy in there is 2.35%. Suppose I said to you, what IQ would you need to be in the top 2.5%? Right, well, the top is over here. So I'd get that guy and I'd get that guy and they add up to 2.5. So my answer in this question would be that you need to be an IQ of 120 to be in the top 2.5%. So once you've filled in all of these pieces, think of it as like a cake. If they if they ask you for the top 22% or the bottom 40% or whatever it is, you can just add up the pieces of the cake that adds up to that number. So if they're talking about 26%, those three guys add up to 26%, and that's the score. If they wanted the top 5%, those two guys add up to 5%, and that's the score.
So I think I found the mistake. So on my bell curves that I wrote down from the lectures, that 2.35 was 2.14.
Oh, that's because I can't count. Change it to 2.35 and everybody will be happy.
Okay. And then the 0.15 was 0.13.
Make it 1.5 because the two of them together make the 2.5. I think what I probably did is I knew they added up to, and I just split them wrongly. I gave more to one and less to the other.
Yeah, because now, if you look at the two side ones, if you have 2.14 and 0.13, it's 2.27.
Yeah, it doesn't add up right. Yeah,
exactly. So that was kind of like where I wasn't understanding.
Okay, does that help?
Yes, sir. That helps so much.
You might want to go online and get a pre-made one with all the numbers in, nice and clean, and print that out. Okay, I think it's time for us to get started, everyone. So we spent a fair amount of time yesterday getting used to scatter plots and associations. And now we're going to look at some of the questions on the homework, and just make sure that I'm on the right place. I am. And so here we go. So in this case, you're going to be given in question 1, for each of the following pairs of variables, is there likely to be a positive association, a negative association, or no association? Now, a positive association would mean as one of the variables gets bigger, so does the other get bigger. So a child's age and their height would be a positive association, right? A negative association would be as the first variable gets bigger, the second variable gets smaller. An example of that might be the age of a car and how much you could sell it for, right? Would you give you a 2-year-old car, you probably get a lot of money for it, but a 10-year-old car, you know, a couple of thousand if you're lucky. That would be a negative association. And a no association would be that the first variable has no effect on what value the second one is. So an example of that could be the x-axis is your age, and the y-axis is the last 2 digits on your cell phone. So can you imagine plotting your age against the last 2 digits of your cell phone? Right, James, you might be 02, right? And I might be 47, right? Would you agree that's probably very random? There's no pattern, no association.
Yes, sir.
So here is our first one. The amount of alcohol consumed and your performance on a test of coordination, where a high score means you're better coordinated, which I would expect, right? So the more alcohol you drink, do you think that you will get a better score on coordination or a smaller score? That's the kind of question you ask yourself. More alcohol, better coordination or less coordination?
Yeah, negative association, right?
Negative association. So you pick the negative, and then I know they give you 2 of them, but one of them's the right one. We expect a negative association, but since we expect the coordination will decrease as the amount of alcohol increases, right? One gets smaller as the other gets bigger. What about your height and your GPA? Do you think there's a connection between how tall you are and how big your GPA is going to be? Anybody want to chuck in an answer on that one?
No association?
There'd be none, yeah. I don't think tall people are cleverer or stupider than short people, right? I don't think your height has really anything to do with your intelligence. And this one's a good one because you have to think about it. The weight of a car and its miles per gallon. So as a car gets heavier, does it have any effect on the miles per gallon you're likely to get from a car?
Absolutely.
Right. Would you agree that the heavier it is, the smaller the miles per gallon is?
Yes, sir.
So that is a negative association then, right? One gets bigger, the other gets smaller. Here's some more stories, similar details. Right, here's our next guy. If you want to see the numbers, they're here, but I don't. This figure, this scatter plot, has Y, the average math SAT, and the X is the percentage of graduating students who took that test that year. So every single one of these dots represents a single state in America. So let's randomly pick one. If you picked that dot there, the percentage of high school students who took the SAT would be what, about 85? Probably get a little bit more detail. Yeah, it's about 83, right? If you click on it, it gives you some number description, right? So let's show that, 83. And what did you get? The average SAT would be 476. I'll take your word for it. When you look at this scatter plot, let's look at association. are these sets of dots positive, negative, or no association? Just by looking at the dots in the scatter plot. Positive, negative, or no association?
Negative association.
I agree with you. You agree it's not great, but isn't it going downhill? Right? I would say weak. If you wanted to put, they don't ask, but if they wanted, I would say it's a weak negative association, but it is negative, right? Which means that the higher number of people who take the SAT, the lower the average is in that state. And then you could think to yourself, side question, I wonder why that's the case. Well, if you only let the most academic people take the SAT, would you agree that if only the most academic students in a state were allowed to take an SAT test, wouldn't you get pretty good results, and so it'd be high? But that would be a very small percentage of all the population, right? And so what that is telling me here is that because different states have different rules about who takes the SAT, that you shouldn't really use this data and say, oh, let's pretend that that state there is Florida. And let's suppose that that state of way up here is New York. You cannot say, oh, New York is doing great because look at the average SAT, it's about 600. Florida is doing horrible. Their average students only get 476. And the reason you can't say that is you're not comparing like with like. See, in New York, maybe only the top 1% of students take the SAT. Wouldn't that mean they get a really good average? Because they're clever and they're good at tests. In Florida, since almost every single person, good at academically or not, takes that test, isn't that going to reduce the test? So people could use this table and then use it as evidence for something that's not true. Florida's horrible, New York's great. Now, I'm not saying that Florida or New York are better or worse than each other. I'm just saying don't use that table to prove it, because it's not comparing like with like. And, well, that's good. Now, about what was the highest average SAT for the 50 states? Oh, and by the way, it wasn't New York. It's the District of Columbia, DC. Oh, well, let's find out. It's up there somewhere, right? You agree that's dot that my mouse is pointing, it's the highest. So if I click on this, there we are. Can you see that I can get the numbers? Because sometimes it's hard to read them. And the highest one was 601. Now, approximately what percentage of graduates took this test? Well, if we go back here, 5%. Now, it then goes on and say, what was the lowest one? And the lowest one was this guy down here. And what was that? That was 476 and 83% of the students. So the average they got was 476, but 83% of all students took that test. We're done. Okay, now I have a bit of an issue with this, but real data does that. You don't get perfect. Here is a scatter plot where you're measuring the height of someone and essentially their head circumference, right? And what I see is, would you agree that this data is pretty random? It's all over the place. And so what that is telling me is I don't see any association. So I don't think tall people have big heads and small people have small heads. I think the size of your head, looking at this data, isn't the size of your head doesn't really affect how tall you are or vice versa. And then they hit you with this guy. One data point appears to be an outlier. And it's quite hard but I can see one guy who's distinctly different from the rest. Now, when you do scatter plots and you talk about outliers, you're really talking about any data point that is outside the norm, right? Is different looking in some way. Can anybody tell me where the guy that I'm talking about is?
Would it be the point at the top of the y-axis?
Yeah, can you see my mouse pointer pointing at it? You might not be able to see my mouse pointer. Can you see the guy he's talking about is up here, 62, 61? Do you see it?
Yes, sir.
Right. So do you, but just curious, do you see my mouse pointer?
Yes, sir.
Oh, good. So I've been moving mouse pointers around for a while, not knowing if anybody saw the darn thing. Right. So we have an outlier, and the height would be, well, if I click on this, it'll tell me, won't it? 61, and what's the other number going to be down here?
62.5.
Oh, I won't argue with that. 62.5, and did we agree on a 61? Yeah, 61. And if you're not sure, sometimes if you click on the picture, it does give you some, some numbers that might well be it. There we go. Can you see it at the bottom there? 62.5, 61. So works perfect for me. So I would describe, I know they haven't got these questions, but I'm going to chuck in my own. I would describe that as no association with one outlier. Agreed? I don't see any shape here. Now, let's look at this shape. It's definitely horrible data, but I think I can detect a pattern. Would you agree that it is positive?
Yes, sir.
Now, it's not great, so you might want to stick the word weak in front of it if they gave you that option, but it is positive association, right? So as the pulse rate before marching gets bigger, the pulse rate after marching. So I guess that means, like, if your heart is already beating quick and you do a big run, it's going to beat even quicker, right? It's, one gets bigger, so does the other. And according to the Mayo Clinic, normal resting pulse for an adult is between 60 and 100. And for well-conditioned athletes, wow, it's 40 to 60. Using this information, explain whether there are any outliers in this data. So, are these people, what do we know about these people? Anything? So, if I say that they're going to be 40, what's the numbers again? 60 to 100. If you do 60 to 100, no, you can't do it here. If you imagine a little wall here, vertically, you see that wall here, 60, all the way to 100? All those guys, aren't they within the range that you would expect someone to be, according to the Mayo, right? 60 to 100, which means that there are 3 outliers based on their definition, right? They're saying you should be 60 to 100 on your pulse rate at the bottom here. So that means all these guys and everybody to the right are fine. So that means I've got a problem here, a problem here, and a problem here. And what guys does that end up being? Okay. 40, I'll probably click on it. So 4457 is definitely one of them. Let me check that. Yeah, resting. That's resting. So my answer would be 46, 65, 55, 65, and 56, 65. Do you have anything that looks like that? Yeah. So according to them, there's 4. I thought there'd be 3. So I wonder who the 4th one is. Right, if you draw that line here, oh, I wonder if that one counts. They say 60-60. I'm definitely happy about those three. I'd probably argue about that fourth one, but it's a judgment call, so it's that one. Okay, now you're going to be given data in the form of a table, and you're wanting to make scatter plots, but there's going to be a lot of information, and you only have two axes. The x-axis is one of the variables. The y-axis is going to be the second. So here we have various places in America, and we're told their latitude, and we're told their August temperature, and we're also told their January temperature. And draw a scatter plot of August being the y-axis and x being the latitude. So I'm going to hit the salt button. Okay. And I want a scatter plot. So I'm going to go to charts, and I'm going to go to scatter plot. And the x variable is latitude, and the y variable is August temperature. Do you see how I chose what they said, right? X is latitude, y is August temperature. Now I'm going to shrink this thing up so you can actually see the thing. There. Can you see that this scatter plot is pretty much negative association? It's going downhill. Mm-hmm. If I click on this little box, it sometimes visually helps. Can you see, they call it a regression line. Do you see it's basically a line that kind of sort of shows you what the data is doing in general? Is it a little bit clearer now it's pointing downhill? Mm-hmm. Right. So back to what find my question here. Back to my question now. Do you see they give me 4 pictures? And one of these 4 pictures is the right one. So right now it's either this picture or this one. Agreed? Aren't they the only 2 that are pointing downwards? And so if I go back to my first picture.
I wouldn't agree with neither of those that you chose.
Oh, well, see the dots that we've got, right? In particular, do you see these 2 little guys here? Mm-hmm. Right. I'm going to bring the big guy in.
Wouldn't it be that one right there?
Yeah, that's the one I would be picking. Yes. So you would agree with that one?
Yes.
Yeah, that's the right one. I don't know which ones I hit the dots on, but yeah, that one fits. So you may have to use a little imagination, right? Now, in this pattern, is it, that's a good question. Linear or curvilinear? Oh, God in hell. I want this regression line out of the way. I could be wrong here, but not because I am wrong, but my judgment call might be different from theirs. If you look at this data, my view is that it appears to be linear and that the association is negative. Would you agree that this data looks more straight than it does curved?
Yes, sir.
Now that's a judgment call. They might see a little bit of a curve up here. I don't, but they may do. So the good news is, don't you have 5 guesses? So if linear doesn't work, won't your next guess be curvilinear? So you know you're going to get it right. And then you can say to yourself, I wonder why they think it's curvilinear. I believe that is linear, and I'm happy with that. I'm going to go out and in now to kind of convince myself that I did, in fact, choose correctly. Come on, Scatterplot. Here we go. Is it about question 6? There we are. Oh, and let's put the answer in. And let's do question 6. And didn't they agree with us? Right picture? and they said linear and they say negative, I am happy. Now, I think you can get away with this when it says, are there any cities that appear to be outliers? Now, when you look at this data, right now, it's going to be a judgment call. And what I mean by that is that you look at the data and you can sometimes argue, yes, it is. And sometimes you might argue, no, it's not. So when you fill this box in, you're going to say why you think it is or is not an outlier. So I'm going to look at this data set here, and let's make the picture nice and big. So I only need to focus on this guy. Oh, I didn't realize it would do that if you went bigger. Okay, let's look at this guy here. If I was going to find an outlier, see that guy there that my mouse is pointing at? I think that might be an outlier. Now, I'm not 100% sure, but doesn't it look kind of too much to the left and kind of isolated a little bit, but not an awful lot? Right, so that one is arguable. Now, can you pretend for a minute that where my mouse pointer is right now, right up at that top right-hand corner, see if there was a dot there. Shouldn't all of us agree that is definitely an outlier? Right, so some situations we all agree, right? So if there was one away over at 50, 100, right, a dot up here, that would be, yeah, you're weird, you're an outlier. This one here is a maybe outlier, okay? I'm going to say it is, you might disagree. So Beatrice, you're in this spot. You're allowed to disagree with me. Does that guy look like an outlier to you, or does it just look like one of the other dots? It's not that special.
I think it looks like an outlier.
Reasonably confident, but not 100%?
Not 100%.
Yeah, and that's okay, because right now we don't have a test. Remember,
Yes,
we have remember with the test that says if the Z score was bigger than 3, you're an outlier, and then you didn't worry about it because everybody said it was. And didn't we have one for the, you know, the upper and lower fence, the upper and lower bound, when you did the 5-figure summary? We had a test. We don't have, at least you won't know about it, we don't have a test for is this an outlier when you do a scatter plot. So you are going to have to do your own judgment call, and sometimes we'll agree and sometimes we'll disagree, and that's totally okay. Now, in question 7, it's basically the same idea. So pick a data set and then choose what it is. And this one, okay. If any of you ever get into real estate, one of the things that you're going to be asked to do by one of your clients is, how much can I sell my house for? You know, what do you think you'll be able to get for it, right? That would seem a reasonable question. And a lot of real estate people have software and they do things called comparables, right? They look for houses like yours that sold in the last 6 months or a year and said, well, that one sold for 250. Your house is pretty similar. You'll probably get 250 for it, right? They kind of do this. But we're going to do a much more scientific version. What you have here is Orange County, California. And as little as I know about America, isn't that where all the rich folk live? Isn't that, well, actually, isn't almost all of California ridiculously dear for houses, right? They're all expensive. And one of the biggest and most useful numbers on predicting the price of a house is its square footage. Would it make sense that a 4,000 square foot house is probably going to sell more than a 1,000 square foot house if everything else is pretty much the same? So they've collected data on square footage and what they were being sold for. So this house here is, what, 443,000. This one here is 1.6 million, right? So I'm going to hit use. Right. Here we go. And then distribution, not distribution, sorry, charts and graphs, scatterplot. And the first variable was square footage. And the second variable is asking price. And let's, there, maybe one too many. Here is the data. Now, do you see there's a whole load of numbers over here? And then there's this guy. You see the one at the top right-hand corner? James, you're not going to argue with me because I'm right. See that one in the top right-hand corner? Isn't he an outlier? Would you agree?
I
He
agree with
has.
you on that one. Yeah, I would
Yeah,
definitely agree with you on that one.
Nobody's going to argue about that one, right? Agree, Tris? Nobody's going to argue about that being an outlier. Unfortunately, if you plot that data point, isn't it very difficult now to see if there's any pattern in the dots that's left? Because all the other dots are kind of crushed into a corner. So how do we deal with that? Well, let me show you what we would do if I could close, hopefully not both these off, right? So here is the house. Oh, if you want to see who he is, that's the one that's causing the trouble. Do you see how big it is? It's like twice the size of everybody else. And it costs, what, 3 times more or 2 times more than everybody else. That's causing a big problem. So what I'm going to do is I'm going to hit use salt. And you are allowed to do this in salt, which is really clever. Can you see square footage and asking price? If you know a data point is an outlier and that it's distorting your ability to see patterns, go down here and delete it. And are you sure? Yes, I am. And you see it's now gone. And when I go back and do charts and graphs and I do the scatter plot and I do square footage against asking price, I can now get a clearer picture on what's going on. And something quite interesting is going on. I don't think there's much of a pattern anymore. Would you agree that some small houses sell for a lot of money and some big houses don't sell for quite as much? So evidently in Orange County, the size of your house doesn't really bear a much resemblance to how much you sell it for. And I don't know a lot about California, so let me make up a story. If you've got a little house and it's by the beach, aren't you probably going to get more money than if you've got a big house next to the motorway? So couldn't location also be a big factor in what your house costs you? That'd be my guess at why I can't see a pattern. That's quite a cool question. I like that one. Oh, and now we're moving on to calculations. So I'm going to have to leave this for a minute and show you kind of what's going on. Imagine that you have a scatter plot, and let's just say for argument's sake, it looks something like this. We can find a single equation that basically is the equation of that line. Do you know that little line that I drew and it put it in? We can get the equation of that line and software will do it. And let's suppose X happens to be the height of an adult. And let's say Y is their weight. And we get a formula that says that the average weight of someone is equal to negative 250, weird, plus 6 times their height. And once you've got that formula, you can then use it to estimate what the average weight of any person within a reasonable amount. So I would like to know what the average weight of a 5-foot person is. Now the height has to be in inches, so I do a quick calculation and I turn it into 60 inches. And so the average weight will be negative 250, add 6 times 60. And so that would be negative 250, add 360. And the answer I got would be 110 pounds. So the height would be in inches and the weight would be in pounds. So from this scatter plot, you create a single straight line that's the best fitting line. The software does it. The software then gives you a formula that says you can now predict what the average weight of a person given their height. So let's suppose, oh God in Himmel. James, do you know your weight?
My weight is 225.
Right. I'm going to use this model to predict your weight, and it's not going to be perfect, but I hope it's at least close, okay? So the average weight of someone of your height, right, is going to be negative 250 plus 6 times their height. What's your height in inches, James?
Well, the last measurement I took was from the Navy, 6'1".
6'1". So that 6'1" is 73 inches. So that's negative 250, 18, 438. And that's going to be, that's going to be 182 pounds. So I wouldn't say that's a very good fit, but you know, it is an average, right? So there are going to be people heavier than 225 and others less than 225. But on average, it's going to be about 225, according to this model. Now, if any of you have kids or had kids, James, you've got children, don't you?
Yes, sir.
Right. One of the things they'll do with your kid when you go in and get a checkup, don't they check your child's development, let's say your child's height, right, how long or how tall they are, with their age? Right?
Yes. So
And
they do
so-
their height and weight, and then their percentile for
Right.
their height and weight among other people.
Right. Well, there is a formula for children, not this one, but there are formulas for children where you put their age in, right? And it'll tell you what their average weight for a boy would be, because boys and girls are different, right? So if your boy is like 32 inches, you plug it in, it'll tell you its weight. And what that allows them to do is they'll be able to say, your child is developing exactly like a 3-year-old is, right? He's about the same height. When they say percentiles, they might say he's the 80th percentile, which means he's a bit tall for his age, right? Or he's the 40th percentile. He's a little bit short for his age, but you know, nothing to worry about, right? And these numbers, these percentiles and these numbers are created by Scatterplots. What they have done is they've collected tons and tons of data about the ages of kids and what they weighed, and the ages of boys, right, and what their height was, and you know, anything else that they find important. And once you've got the equation, you can plug your child's age, and it will tell you the typical one in the middle, and then they can do percentiles away from that. So that's that's one of the ways they can use this. Now, back to this one here. One last piece of information that we can get from this formula. In mathematics, this number here is sometimes called the slope. So can you imagine it was this data here, that line would have a slope of 6. We can use it to say the following. For every 1 inch increase in height, so every time that height gets 1 more than it used to be, your weight will increase by that number, the slope, 6 pounds. Now, obviously, adults don't increase in height, but when you're still growing, what that is saying is that every inch that you grow, if you're still growing, you're probably going to get 6 pounds heavier. It doesn't mean you're getting fat. It just means taller people weigh more than shorter people, right? And this rule is based on that number. Now, if that was 4, for every 1 inch that you increase in height, if that was 4, your weight would increase by 4 pounds. Are we good with that?
Yes, sir. So is that negative 250 plus 6 height? Is that an actual formula, or is that just an example used for these questions?
That's the one that they gave me. So I don't always know where they get these formulas. I'm assuming that they went and looked up a report somewhere and collected the data.
Oh,
So,
okay.
right. Now, let's use your value, James. Your real weight was 225 pounds.
Mhm.
This formula predicted your weight, and it wasn't right, which is what you'd expect. It'd be a miracle if it was exactly the right number for every human in the world, right? Because even at the same height, aren't some of us fat and some of us skinny, right? But what you might want to know then is what's called, it's got a fancy name, it's called the residual. And the residual is the difference between the predicted error and what the real error is, right? So what the real value is. So if you did 102, take away 225, in this case, you would get what, 18, 43, and it would be negative 43 pounds. So the residual would be, you predicted 43 pounds less than it really was for James. And we call that the residual. I would probably call it the error if I was making the name up, but it was the residual, right? Now, I'm going to show you a completed version of that question. And it's down here as question 10. Now, here is the average weight story. Suppose someone is 70 inches. Can you trust me? If you plug it in there, the answer is 170 pounds, right? Now, that person was really 175. So what did you do? You put in the predicted weight and you took away, the real weight, and you took away the predicted weight. And in this case, the answer was 5 pounds. So you were 5 pound out. Now, if I switched it round, I guess it would be negative 5. Are we cool with that? Residual. How far out were you in your model? Okay, next one is, these are very visual, so I really do have to show you the homework questions. Otherwise, I'd just be drawing dots in midair and it wouldn't be very clear. Let's try that again. Gotcha, right. This data that we've got here is the same data that we used earlier. So there was Maryland and can't remember, Washington State or whatever up here. And the average SAT score in math is 571, take away 1.1, the percentage you took the test. So the slope of this line is negative 1.1. So there we are. And what that tells us is right? So the slope is negative 1.1. And they ask us to interpret that. Well, for every extra percent of people who take the test, the average will go down 1.1. And that's that guy there. And in a certain state, only 9% took the test. So you go to the calculation and 9% took the test. So you change that to 9, you do the calculation, and that's the number you get. So that would be the predicted SAT score that state with 9% of people taking part. The actual answer was this guy. So you would do 574, right? The real answer. Take away the predicted answer, which is 565.01. And there you go. There's that guy we called a residual. That's where it came from. So put here the real score, take away the predicted score. That's pretty much the same question. Very similar type of question. I'm just scanning in case anything I've got. Okay, that one I need to do. You might wonder where they got these equations from. So imagine that we had a scatter plot and 30-year-old people had this blood pressure and 55-year-old people had this blood pressure. So on my scatter plot, I have got lots of dots, but I just picked that dot there and that dot there. And I'm now going to find the slope joining this point to that point. Okay. Now, this involves you doing stuff that you did a while back. So let me try and remind you how it works. The slope is the rise divided by the run. You remember that? Slope is rise divided by run. So this distance here would be the rise. And this distance across the way would be called the run. $130, take away 115. What you do is you subtract the two y coordinates. And then 55, take away 30. You subtract the two x coordinates. And that's the formula. Subtract the two y, subtract the two x. So on the top, I have 15. And on the bottom, I have 25. And that can simplify down to, what does that? 3/5. So there's the slope.
And it doesn't matter which 2 points you pick to do that.
As long as you're consistent, right? So by that, I mean these two and then these two. So you can go that, take away that, divided by that, take away that, and it'll work. Or this, take away that, and this, take away that, and it'll work. As long as it's the same order, right? Second coordinate, take away first. Second, take away first. It's fine. If you mix and match them, you'll get the sign wrong, right? You'll get a plus where it should be minus or vice versa. So far, so good. Now, way back in the day, we had the equations of lines. And if I know the slope, which I do, is 3/5, then y is equal to 3/5 x. What I'm now going to have to do, this is probably the only time you're doing anything that even vaguely looks like algebra, is to find out what number b is. So take either of the 2 points, it doesn't matter. Call this guy x, call this guy y. Write down the equation with the slope already written down. Put in y here and put in oops, and put in 30 here, right? X is 30, y is that? So I now have 115 equals 95ths plus b. 115 equals 118 plus b. Yeah. And that gets me 97 as b. So I now have the equation of the straight line. It's 3/5 x, which is the slope, plus 97. And all I'm going to do now is change the x and the y into what they are. In the story, they told me that x is the age. And in the story, they told me y is your blood pressure. So I've now created one of those equations that we've used in a couple of the earlier questions. 3/5 your age plus 97. And so to finish with, they say, well, what would you think the blood pressure for someone who is 35 years old? Well, the predicted blood pressure would be 3/5 of 35 plus 97. Does that get me 21 plus 97? And that would get me 118. So I would be predicting 118 as their blood pressure. And just to show you that I actually got it correct, that 0.6 is just 3/5 written as a decimal. So that's the slope. And there's the answer, 118. And this one is back to the easier ones where they give you an equation and you plug in the numbers and see what works. Ooh, that should have a salt button in it. Okay. I didn't realize that one's there. Right, here we have a scatter plot. Oh, thank goodness. They told you the equation. The number that goes here, right, the one that's next to this variable is the slope. So basically the slope goes there, and then the rest of the questions are pretty straightforward. And here's another one of those questions. Here we go. Predict what certain values are. I think we're almost done. Yeah. Here is an equation. So this is y and this is x. So if you want to know what 9.9 would get you, negative 7.69 plus 3.23 times 9.2, and that's what you would get. Oh, last question. Perfect timing. Here is some data where they've looked at the circumference of a tree and compared it against its height. And so I'm going to use the salt button. And this is how you would use the software to get those equations that we've been told what they're equal to without really saying where they came from. So if I go to charts and graphs and I do a scatter plot and circumference against height, there's your guy. Shrink it up. There you go. There it is. Well, that's a pretty good one. It's a little bit curvilinear, but it's pretty good. Now, where do they put the numbers that make the equation? They're kind of well hidden. Do you see the slope and the guy that they call the intercept, right? So in this question here, y is the height and x is the circumference. The intercept is the number negative 13.1189 and the slope is 9.4673 times circumference. Right, let me show it. actually, last question, so it's pretty good timing. I got those numbers by looking up what they called the y-intercept, which ended up being negative 13.1189. And right next door to it, they had another number called the slope, which is 9.4673. The height, which is the y value, that is where the y-intercept goes, the number on its own. And that's where the slope goes, times whatever x is, and x is the circumference. So I now know that the average height of a tree is this number plus 9.4673 times the circumference. So let's suppose I have a tree and its circumference, which is something I can measure relatively easy, was say 10 inches. Then my predicted height for that tree would be negative 13.1189 plus 9.4673 times 10. So it would be negative 13, that guy, plus 94.673. Oh, let's make my life easy by pretending it's to the nearest whole number, in which case 82 inches. So I can now use this information to predict what the height of a tree whose circumference is 10 inches. Now, if that was a good model, right, if the data was really nice and tight, these predictions, right, predicted heights would be pretty accurate. If you tried to measure the height of a tree and you wanted to do it, I guess isn't the only way you could do it would be climb up the tree with a very long tape measure and then dangle it in the bottom and hope you don't get killed. In this case, couldn't you just simply measure the circumference of the tree and then plug this formula in and say, it's going to be about 82 inches, give or take a few. And now you have an answer that is pretty reliable and a lot less dangerous to collect. But last name for attendance. While you're doing that, your excuse me, your online test 2 is now available, as is your homework. And all of that homework has to be completed by midnight Sunday. So